this section, we'll be looking at how we can use a polynomial function to model or approximate some other kind of elementary function. Since polynomial functions are easy to integrate and differentiate, this can help us if we have a difficult function to perform those operations on. Our first step in finding this polynomial function is to pick a polynomial function that has the same value as the other function at a particular point. We're going to call that point C. So what I want to do is pick, for f of c, some value of the function. I want a polynomial function where these two have the same value at this particular point C. The next step is to make the first derivatives at point C also equal to each other, so that f prime of C is equal to p prime of C. Let's take a look at how this works. I'm going to start with the function f of x equals e to the x power. So I want to find a first degree or a linear polynomial function, which I'm going to call p1 of x, and it's going to equal a sub 0 plus a sub 1 x. This is just a linear function. Mx plus b is how we usually write it. But in this case, we're going to pick a sub 0 and a sub 1 so that they match, and that f of c is equal to p of c, and also f prime of c equals p prime of c. Okay, so let's go ahead and let c be 0. So I have f of 0 is equal to e to the 0 power, which I know is 1. So I want p of 0 to also equal 1. In addition, f prime of 0, I know that the derivative of e to the x is e to the x again, so f prime of 0, e to the 0, also 1. Okay, so looking at the conditions that I've set up, if f of 0 is 1, this term is going to be left out, and if p of 0 is going to be 1, then a sub 0 has to be 1. So a sub 0 is 1, and then I know that a sub 1 represents the slope or the first derivative, so that's also going to have to be 1. So my function p of c is equal to 1 plus x. If I were to draw a graph of these two functions, it would look something like this. To see these two functions together on the calculator, I can start by pressing y equals. And if you're not familiar with this emulator, anytime a button turns red, that's the last thing that I clicked. And down here at the bottom, it shows you what I've done. So y equals, and we're going to start with e to the x. So here's e to the x in blue. So second e to the x. And then I just have to put that x in there. So alpha x, and then enter. And for my second function, the p of x, I'll put in 1 plus x. Okay, once I've got my two functions in here, I click on Graph, and there you can see the two functions together. Okay, here's the e to the x, and here is the 1 plus x. And you can see right here at 0, they intersect, and it's a good approximation just for this little area near there. And we'll come back to this and see if we can get a better approximation. I'm sure that some of you looked at that, what I call the first approximation of the function f of x equals e to the x, and say, well, that's not much of an approximation. Touches the graph one place, and it's not even a curve. Okay, and so this is just really a very rough approximation. We're going to look now at how we can refine it by taking higher order derivatives. In this case, we're going to continue with what we had before, where f of c equals p of c, and that f prime of c equals p prime of c. But we're going to add a third requirement, that the second derivative also has to match. So f double prime of c is equal to p double prime of c. Okay, the format for p double prime, we know that f double prime of c is still equal to e to the x if we use that same function that we had. To make the second derivatives the same, I want x here, I can use this form. I have 1 plus x like I did before, but to make the second derivatives the same, I'm going to have to add 1/2 x squared. So now this is a second degree approximation, and you probably can tell this is a quadratic function, so at least it's got a little bit of a curve to kind of match the curve of e to the x. In general, I can say that p of x has to equal 1 plus x plus 1/2 x squared plus 1/3 factorial x cubed, and so on. And my general term would be 1/n factorial x to the n power. Okay, and this is what we call a third, or this much would be a third degree approximation of with a polynomial function. Okay, so we're going to take this much and use it to make a table to compare the third degree polynomial. I'm going to go back up to this first one and highlight the equal sign and then click. That'll make it so that one doesn't show up in our table. And now I'll put in the third degree equation, which is 1 plus x plus 1/2 x squared plus 1 divided by 3, and I want 3 factorial. So to get the factorial, I have to use the math key and go 1 to the left. That gets me back to probability, and here's a factorial right here at choice number 4. So now I've got 1 over 3 factorial, and when I'm using the calculator, I have to put in the multiplication symbol even though we don't write it. And then I get x again, and I raise it to the third power. So this is my third degree polynomial. Once everything's in there, I can go to graph just to take a look at it, and I see that the graphs are much closer together than the linear was. But what I really want to do is look at the table. So I click on second and the graph button again, and it gives me a table. Okay, my table is already set up for tenths. If you need to do that, use second and this table set, and you can change this table start right now is at 0.5, and I'm going to change that to negative 0.1. And make sure you're using the negative symbol and not the subtraction. Negative 0.1. Actually, I'm going to use negative 1 for the first row of my table. And my delta table is 0.1, so I'm going to go up 1/10 at a time. Got everything set the way I want it. And so second table. In this first column are my x values. This is the e to the x function. And this is the approximation we did with the cubic equation. And you can see at negative 1, the e to the x is 0.36788. The approximation is 0.33333. Not really very close. But let's scroll down. The next value in my table, I'm going to use negative 0.2. And here my values are much closer together, 0.81873 and 0.81867. If I scroll down once more, 0.90484, 0.90483, so even closer. When I'm at 0, the values are the same, and that's the way I set up the polynomial, is so that the values would be the same at 0. At positive 0.1, I can see the values in the calculator are the same. If I took it out far enough, they wouldn't be, but they're still very close. And then at positive 0.2, again, the values don't differ until the last decimal place that's shown. So very close. And then as I get further away and go maybe to x equals 1, I see that my values are starting to spread out a little bit. But right around 0, the values were really quite close together. In our last example, we worked with c equal to 0 just for convenience. But if we want to have c equal to some other number, we can write our polynomial like this. P sub n of x is equal to a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared plus a sub 3 times x minus c to the third. This 2 goes out here. And then the first derivative of this polynomial, the a sub 0 would drop out, and I'd have a sub 1 plus 2 a sub 2 times x minus c plus 3 a sub 3 times x minus c squared, and so on. My second derivative then would look like this. 2 times a sub 2, and this would drop out when I take the derivative, plus 3 a sub 3 times 2 times x minus c to the first power now, all the way up to n times n minus 1 a sub n times x minus c to the n minus 2 power. And I can continue on taking derivatives and just following this pattern. If I then let x equal c, if x equals c, all those are going to drop out. And p sub n of c is going to equal a sub 0. P prime of sub n of c is going to equal a sub 1. And the nth derivative of p sub n of c will equal 2a2, and we're just going to continue on in this pattern. a1, 2a2, 3a3, and so on. In my general form, the nth derivative of p sub n of x would be equal to n factorial times a sub n. When I have this form, we call this a Taylor polynomial. Okay, and if C equals 0, then I get this. And so on. And this form is called a Maclaurin polynomial. So we have two kinds: Taylor polynomial where C is not equal to 0, and a Maclaurin polynomial where it is. So going back to our example, f of x equals e to the x. We want to write the nth Maclaurin polynomial for this function. So again, we're assuming that c is 0, and so this would be f at 0 plus f prime at 0 times x, f double prime at 0 over 2 factorial, which is just 2, times x squared plus f triple prime 0 over 3 factorial x cubed, and so on. And then our last term would be 1 over n factorial times x to the n power. Okay, so this is our Maclaurin polynomial for this function. In this example, we're going to look at the function of natural log of x instead of e to the x and find a Taylor polynomial for it. So I have f of x equals natural log of x, and I want a Taylor polynomial. And actually, I want to find p sub 0, p sub 1, p sub 2, p sub 3, and p sub 4. And after we've found these, we're going to put them all in graphing calculator and see how the approximation gets better and better and better the more derivatives we use. So we're going to center at c equals 1. So if f of x equals natural log of x, we could say that f of 1 is equal to natural log of 1, which is 0. Okay. F prime of x would then equal 1 over x. and f prime at 1 would then be 1 over 1, or just 1. The second derivative would be negative 1 over x squared. So that value would, at 1, would be negative 1 over 1, or negative 1. The third derivative would be positive 2 over x cubed, 2 factorial, which is just 2. And so the third derivative at 1 would be 2 factorial over 1, or just 2. Okay, and I could go on with that. They asked for P4, so I need to do the fourth derivative. Let's do that up here. The fourth derivative would equal 3 factorial over x to the fourth. So at 1, the fourth derivative would be 3 factorial is 6, and that would be 1. Okay, so let's just condense this down to what we really need. Okay, so f of 1 equals 0. First derivative is 1. Second derivative is negative 1. Third derivative is 2. And then the fourth derivative is negative 6. This should have been negative. Okay, so I've got all that information there that I need. So to write the P sub 0 Taylor polynomial, I just have to use that F1, and that's 0. P sub 1 of x would be f of 1 plus f prime of 1 times x minus 1. Remember, we said we were centered at c equals 1, so we have to subtract that. And f of 1 is 0, f prime of 1 is 1, so this is just x minus 1. So that's our answer for P sub 1. P sub 2 of x is going to be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared. Okay, and again, this is going to drop out. F prime of 1 is just 1. So I could write this as, just move it over here a little bit, x minus 1. f double prime of 1 is -1, so it's going to be minus 1 over 2 x minus 1 squared. So that's p sub 2. And using the same pattern, p sub 3 is x minus 1 minus 1/2 of x minus 1 squared plus 1/3 of x minus 1 cubed. And then p sub 4 of x would have all of this minus 1/4 x minus 1 to the 4th. Okay, we're going to take these polynomials that we've come up with, put them in the calculator, and take a look at how well they approximate our function natural log of x. In the next two examples, we'll be looking at finding polynomial functions that represent trigonometric functions. So we want to find a Maclaurin polynomial for cosine of x. And we're actually going to find p sub 0, p sub 2, p sub 4, and p sub 6. And we're going to use these to approximate the cosine of 0.1. I've got f of x is equal to cosine x, that's my original function. F prime of x is negative sine x. F double prime of x is negative cosine x. And the third derivative I'm back to sine x. Okay, so if I do f of 0, the cosine of 0 is 1. Sine of 0 is just 0, so negative or positive, it's still 0. Second derivative is negative 1. And then the third derivative is 0. And if you continue this on, we're going to continue to get values positive 1, 0, negative 1, 0. Which is why we're only doing p sub 0, p sub 2, p sub 4, p sub 6. Because we're going to get a lot of 0 values and we're going to kind of skip over those. So our derivatives are positive 1, 0, negative 1, 0. The function and the first three derivatives. So now I want p sub 0 of x is equal to 1. P sub 2 of x is equal to 1 minus 1 over 2 factorial x squared. P sub 4 of x is equal to 1 minus, same thing, 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th. And then our last one, p sub 6 of x, is everything we had before. And then our last part would be, not plus, minus 1 over 6 factorial x to the 6th. If I substitute my value 0.1 into this polynomial, it's approximately equal to 0.995004165. And if you put this in your calculator, it should be the same up through these first 9 decimal places. Next, we're going to look at finding it for another trig function, sine of x. So we want to find the third Taylor polynomial and our original function f of x is sine of x, and we want to be centered at pi over 6. So if f of x equals sine of x, then f of pi over 6 is going to equal the sine of pi over 6, which is 1/2. Okay, f prime of x is cosine x. So f prime of pi over 6 is the cosine of pi over 6, which is square root of 3 over 2. The second derivative is negative sine of x, so that the second derivative is equal to negative sine of pi over 6, which is negative 1/2. And in the same way, we can find that the third derivative of pi over 6 is negative cosine pi over 6, which is negative square root of 3 over 2. So I'm going to keep just these four numbers that give me the derivatives. 1/2 square root of 3 over 2, negative 1/2, negative square root of 3 over 2. So my third Taylor polynomial, P3 of x, is equal to f of pi over 6 plus f prime pi over 6 times x minus pi over 6 plus second derivative of pi over 6 times x minus pi over 6 over 2 factorial, and this is squared. And then our third derivative would be over 3 factorial and have x minus pi over 6 to the third power. Okay, now we can simplify these with what we know. F at pi over 6 is 1/2. This term, first derivative is square root of 3 over 2. And we'll just leave that for now. Second derivative is negative 1/2. So we've got, make that all one fraction, 2 times 2 factorial. And then the third derivative is negative square root of 3 over 2. So I'm just going to make that 2 times the 3 factorial, like that. Okay, and you can put this in your calculator and see how well it models this function sine x. Okay, so we've been in this section using Maclaurin polynomials and Taylor polynomials to estimate a function that's not a polynomial. And you might wonder, well, just how good is this estimate? We'll be looking at that in the next couple of examples. In this example, we're going to make an estimate using a Maclaurin polynomial for natural log of 1.1. So we want to approximate natural log of 1.1. And we are asked to use the fourth Maclaurin polynomial. And because 1.1 is closer to 1 than it is to 0, we'll be looking at natural log of 1 plus x. So this is our original function. So we'll call this g of x. And so g of 0 would be the natural log of 1 plus 0, which is 0. And g prime of x would be 1 plus x to the minus 1. So g prime of 0 would be 1 plus 0 to the minus 1, which would be just 1. Second derivative of this function is negative 1 plus x to the minus 2, and the value at 0 would be 1 plus 0 to the negative 2. So, negative 1 plus 0 to the negative 2. So this would be negative 1. Okay, third derivative. It's going to be 2 times 1 plus x to the minus 3. So the value of the third derivative at 0 is going to be 2 times 1 plus 0 to the minus 3, which just equals 2. And then our fourth derivative is equal to negative 6 times 1 plus x to the minus 4. So the value of our fourth derivative at 0 is negative 6 times 1 plus 0 to the negative 4, which is just negative 6. So there's all of our numbers that we need for the function. Remember, this is the original function, and these are the first 4 derivatives. So now, P4 of x, following our format, g of 0 plus g prime of 0 x plus g double prime of 0 times x squared over 2 factorial plus third derivative over 3 factorial times x cubed plus the fourth derivative over 4 factorial times x to the 4th. Okay, substituting in the numbers, we know g of 0 is 0, so this can just go away. First derivative is 1. So I can put a 1 there if I want to, don't really need to. Second derivative, negative 1. So all I really need to do here is change that plus to a minus. And I'm just going to write that as x squared over 2 factorial. Although we know 2 factorial is just 2, so we could take that away as well. Okay, third derivative is 2. So I'm going to have plus 2 x cubed over 3 factorial. That takes care of this term. And then my last term is going to be, fourth derivative is negative 6. So this is a negative 6x to the fourth over 4 factorial. Okay, so a lot less complicated now. Okay, let's see what we can do to make it even a little simpler. I'm just going to write x minus 1/2 x squared. The 3 factorial has a 2 in it that I can use to cancel out this 2, and that leaves me with just a 3 here, so plus 1/3 x cubed. The 4 factorial has both a 2 and a 3 in it that will cancel out with the 6 and leave me with just the 4 here, so minus x to the fourth over 4, or 1/4 x to the fourth. So the natural log of 1.1 is approximately equal to the natural log of 1 plus 0.1 which is approximately equal to p sub 4 of 0.1. And when I work this all out, I get 0.095 3083. Okay, and you can compare this value to the value that you would get in your calculator when you just plug in natural log of 1.1 and see that it's very, very close. Two things that you should take away from this problem is that when I use a higher degree Taylor or Maclaurin polynomial, I generally get better results. And the other thing is that if I keep c small, if I stay very close to the value that I want, my approximation is also more accurate. Okay, so we said the two general principles for getting a more accurate approximation are to use a higher degree polynomial and to keep c small. But how good is good? Let's look at how we can find the remainder of a Taylor polynomial, which gives us a range between which our value should be. To do that, we need to look at Taylor's theorem. This is in your book, but I'm going to write it out for you here. Taylor's theorem says if I have a function f of x that has n plus 1 derivatives, on the interval I that contains c, for each x in that interval I, there exists some value z between x and c such that f of x is equal to f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial, and so on until we get to the nth derivative of c times x minus c to the nth power over n factorial plus r sub n of x. Okay, we call r sub n the remainder. And to define it a little better, r sub n of x is equal to f. The next derivative there should be z in here, over n plus 1 factorial times x minus c to the n plus 1 power. Okay, there is a proof of this theorem in Appendix A if you'd care to check that out. Okay, something that comes out of this is that the absolute value of this remainder is less than or equal to the absolute value of x minus c to the n plus 1 power over n plus 1 factorial times the maximum of the n plus 1 derivative of z. Okay, and this max is just the maximum value between x and c. Okay, now if n equals 0, Taylor's theorem says that if f is differentiable in an interval I containing c, there exists a z between x and c such that f of x is equal to f of c plus f of z times x minus c. Or we could rewrite this and say f prime of z is equal to f of x minus f of c divided by x minus c, which you might recognize as the mean value theorem. Okay, let's see how we can use this. We're going to say f of x is equal to sine x. And that lets us know that the third Maclaurin polynomial is x minus x cubed over 3 factorial. Okay, so we're going to use this and Taylor's theorem, we want to approximate the sine of 0.1 and determine the accuracy. So we're going to use Taylor's theorem, which tells us that sine of x is equal to x minus x cubed over 3 factorial plus r sub 3 of x. So we can rewrite that as x minus x cubed over 3 factorial plus the fourth derivative of f of z over 4 factorial times x to the fourth. And this is for z in between 0 and 0.1. Okay, and for sine, so now we have the sine of 0.1 is equal, or approximately equal to 0.1 minus 0.1 cubed over 3 factorial which is approximately equal to 0.1 minus 0.000167. So it's approximately 0.099833. Because the fourth derivative here is sine of z, it follows that the error is bounded by 0 and this is equal to sine of z over 4 factorial times 0.01 to the fourth power, which is less than 0.0001 over 4 factorial, because we know that sine of z is going to be either 1 or less. So this gives us 5 zeros and a 4. Okay, so we could write this as 0.0983 3 sine of 0.1 and 0.09837. So that's our estimation and the amount of error involved in that third degree estimation. As we've done before, we're now going to look at how we can specify the amount of error that we're willing to tolerate in finding an approximation. So let's say we have f of x equal to natural log of x, and that tells us that the n plus 1th derivative of x is equal to -1 to the n times n factorial over x to the n plus 1. Okay, and we want to expand about c equals 1. Okay, we want to find how much of a Taylor polynomial do we have to have for natural log of 1.2 so that the error is less than 0.001. So we want to get our error less than 1/1000th. Okay, so here's our n plus 1th derivative. Let's look at what our remainder would be using Taylor's theorem. Absolute value, the n plus 1th derivative of f of z over n plus 1 factorial times 1.2 minus 1 to the n plus 1. Okay, and we can simplify this a little to n factorial over z to the n plus 1 times 1 over n plus 1 factorial times 1.2 minus 1 to the n plus 1. Yep, that goes here. Okay, now the n factorial and n plus 1 factorial are going to cancel each other out. So I'm left with just n plus 1 in the denominator. And of course, 1.2 minus 1, I can make that just 0.2. Okay, so now my simplified version is 1 over z to the n plus 1 times n plus 1 times 0.2 to the n plus 1 power. And we're going to stipulate that z is in between 1 and 1.2. Okay. In this particular interval, from 1 to 1.2, 0.2 to the n plus 1 over z to the n plus 1 times n plus 1 is less than 0.2 to the n plus 1 over just n plus 1. Okay, z is bigger than 1, so this is going to make the denominator larger than this denominator, so the whole fraction is smaller. So I want to find a value of n so that 0.2 to the n plus 1 over n plus 1 is less than 0.001, which gives me 1,000 is greater than, less than n plus 1 times 5 to the n plus 1 power. Okay, so let's rewrite that up here. Just to be clear, I want 1,000 to be less than n plus 1 times 5 to the n plus 1th power. Okay, and then I'm going to use trial and error. Just pick some values for n. And the smallest value of n that's going to satisfy this is n equal to 3. So if I want to make an estimate that's within 0.001, I need to use at least a third degree Taylor polynomial.